This is Investigating Resistive Forces, Formal Lab 2 by Group 1B. The purpose and main question of this formal lab is how do different liquids affect the terminal velocity of an object? So we know that when an object is at terminal velocity, the mass times gravitational constant is equal to the internal drag friction plus viscosity friction, as those are the two forms of friction that are acting on the object. Using this relationship, we are trying to find how viscosity affects the terminal velocity of the ball. The experiment we did was testing the terminal velocities of the ball bearings in corn syrup, dish soap, and water. We used Tracker to find these velocities. We found that the more viscous the liquid it was, the slower the measured terminal velocity was. And this is true as viscosity directly correlates with the friction of the liquid on the ball. After doing this experiment, we found that corn syrup had the highest viscosity, followed by dish soap, and then water. We also found, by using Tracker, that the velocities of these ball bearings in these liquids were inversely proportional to their retrospective viscosities. And this is true as corn syrup had the lowest terminal velocity, and water, which was the least viscous, had the highest terminal velocity. The physics in this is that given the equation, we already know that mg equals internal drag friction plus the viscosity friction, that at terminal velocity, the force of the object going down due to gravity will be equal to the total amount of friction pushing up on the object. So as an object is at terminal velocity, it's at a constant velocity and accelerating at a rate of 0. We know that the forces pushing down on it and pushing up on it are going to be equal. Viscosity and drag are both included because the objects in fluid experience both of these forms of friction. And due to Stokes' law, the figure on the right, N, which is viscosity, has a directly proportional relationship to the friction of viscosity on the object.
The two models used in this lab were the system schema and the force diagram. In the system schema, the main object in the system and the only object in the system was the ball. The Earth had a gravitational force on the ball, the liquid, and the graduated cylinder. The liquid had a contact force with the graduated cylinder, and the ball and the liquid had contact and resistive forces between them. In the force diagram, at terminal velocity, the force viscosity of the liquid on the ball plus the force drag of the liquid on the ball is equal to the force gravity of the Earth on the ball. This is because it is at terminal velocity. For the experimental design of this lab, we first had to take and record the mass of the ball bearing. Then we filled 3 50-milliliter graduated cylinders with 50 milliliters of water, dish soap, and corn syrup. Then we dropped the ball bearing in each graduated cylinder and record as the ball makes its way through the liquid to the bottom of the graduated cylinder. Then we used Tracker to determine the velocities traveled by the ball bearings in each solution. This experiment allows us to track the terminal velocity of the ball in order to determine the resistive forces on the ball based on the viscosity of the liquid it is falling through. The first error in the experiment was camera movement. Data collection was very difficult for the corn syrup trial especially because the video was a little bit shaky, throwing off the exact position of the ball at that certain time, which leads to the error in Tracker. It was difficult to record the exact position for the balls because it wasn't very clear exactly where the bottom of the ball was, so the exact position and velocity couldn't be accurately calculated. This was especially difficult for both the corn syrup and the water trials because the corn syrup trial moved way too slow and the water trial moved very fast. Human error was also an error because for the corn syrup trial there was a solid layer at the top of the graduated cylinder preventing the ball from falling through, so we needed to push the ball through the layer in order for it to fall through. This may have added a force to the ball that altered its velocity and threw off its calculations. And finally, specifically for the water trial, although tracked correctly, the data showed a terminal velocity during the water trial, even though the bearing should have still been accelerating.
Our data for this lab showed that as the viscosity of the liquid went up, the velocity went down. And as we can see through the data in the table on the bottom, that the higher the terminal velocity, the lower the viscosity of the liquid. So water had the highest terminal velocity and also the lowest corresponding viscosity, and corn syrup had the lowest and slowest terminal velocity and the highest viscosity. In the bottom corner, we can see our calculation for the radius of the ball, where we measured the volume of the ball and calculated for the radius. And in the upper right-hand corner, we can see our calculation for the viscosity of water. The conclusions and scientific reasoning of this is that a higher viscosity makes it more difficult for the ball bearing to travel through the liquid, as the liquid is harder to displace and applies a higher resistive force on the ball. This is because the more viscous a liquid is, the more intermolecular forces it has, and that applies a stronger pressure and a stronger force against in the opposite direction that the ball is falling. Our data showed an indirectly proportional relationship between viscosity and terminal velocity, and Tracker also showed that a terminal velocity was reached in all of the trials, showing a constant velocity and an acceleration of 0. In the figure to the right, you can see our graphs for the movement of the ball bearing in the water, and it shows that it did reach terminal velocity as the velocity is constant and the acceleration is at 0.